So the first theorem we're going to look at is intermediate value theorem, and you actually do look at this one in pre-calc as well, but it comes up more heavily in AP Calc. What I use a highlighter for when I'm teaching this are all of the conditions for the theorems. If the conditions for the theorem aren't met, then the whole thing goes out the window and you can't even use it. You know how you have those if-then statements? The condition is the if part. So it's like, if this, then this. And if the if part is not true, then the then part doesn't even really matter. So you have to have the conditions be met. Also, these, I typed them out the way that they are, like verbatim out of the textbook, and they're written kind of in gibberish, so we're going to sort of decode what these mean and write it in like plain English. So intermediate value theorem says if a function is continuous, so that is your condition. If a function is not continuous on whatever interval you're talking about, you can't use the intermediate value theorem. It won't even apply. So when you're using this theorem to justify things on the AP exam, you have to mention continuity. You have to mention that the function is continuous on the interval. They won't give you points if you don't talk about it. It's that important. It's easy to mention. You just say the function is continuous on this interval, but you have to say it. And so if a function is continuous on the closed interval from A to B, and the C is any number in between f of A and f of B, and that's what between means, intermediate, inclusive, so including those, then there must be at least one value of x in that interval A to B such that f of x equals C. You all got that? And that looks like a lot. So here's what we're going to do. We're going to draw a picture to explain this because I think visuals help a lot. So draw yourself, you know, like a little space to have a graph over here. And just draw yourself, you know, something that goes up and comes back down. It's not real important, just some sort of function that's continuous. So no asymptotes or holes or jumps or anything like that. So just some sort of continuous function. So what they're saying is we have this interval from A to B. So here on the graph, that would be f of A, and then here on the graph would be f of B. So you have 2 points. You have A, f of A, and then B, f of B. So just the input and the output. And so as long as the function is continuous, they're saying C is any number in between these outputs. So we have a C value in between them. It's saying there has to be at least one X value in here that gives you that C value. So this X value has to be there. What this theorem is saying is that this must exist. Is that X value has to be there. So just in plain English, what this is telling us is if there is an output, sorry, I can't write and talk at the same time. If there is an output, then there is an input. Meaning if this C value is there, it had to come from somewhere. It can't exist without there being that X value. And so what this theorem is used to do a lot of the times is prove that there are zeros. What you do is you say, since a function is continuous and this output was negative and this output was positive, zero's got to be in between. If a function is continuous and you have a negative and you have a positive, then zero has got to be in between. So that's what this is oftentimes used to discuss. But it doesn't have to necessarily be zero. You can prove, you know, any number is in between. So just remember, intermediate means in between. You're going to have a value in between two others, and it had to come from somewhere. All right, extreme value theorem. Condition for this one: if a function is continuous. So again, if the function's not continuous, if there are asymptotes or breaks or holes or gaps or anything else, the theorem is not going to apply. So this one says if your function is continuous on the closed interval A to B, then the function has a maximum value and a minimum value on A to B. That one's a little bit easier to interpret. It's just saying that there has to be a maximum and a minimum. If you have a continuous function, you're going to get a high point and a low point. So I'm not going to necessarily draw a picture for that one. But what this is saying, if you want to break it down into, plain English here, there is a maximum and a minimum in the interval or on the endpoints. And we won't do too much with this one, with the examples that we do today. This will come up next class when we do something called the candidates test. And let me just put that in parentheses here, just for foreshadowing. We're going to do this next time. The candidates test is when you're testing for an absolute maximum or minimum, and you test all the critical points and all the endpoints. Those are all your candidates for where you could have an absolute maximum or minimum. And that comes from the extreme value theorem. So if you have a continuous function, you have a maximum and a minimum. Usually the question I get asked somewhere around this point is, but hey, Ms. Cole, what about a constant function? How can that have a maximum and a minimum? And I totally love that question because it means that you're thinking about what this actually means. It does have a maximum and a minimum. It's just really, really, really boring. If you have a constant function y equals 2, then the maximum is 2 and the minimum is 2. So they exist. It's just not real interesting. All right, but it does actually exist. It's the same number. All right, next one, mean value theorem. So this says if a function is continuous on closed interval a to b and differentiable on the open interval a to b. So there's 2 conditions for this one. Your function has to be continuous and differentiable. So let's remind ourselves what differentiable means. Can you type in the chat, if a function is differentiable, what has to be true for it to be differentiable? It can't have certain things in it. What can it not have? Good, nice. It cannot have a sharp edge. And it can't have any discontinuities. We kind of said that already. And then there's one other thing. Yeah, no holes, no asymptotes, no breaks. It has to be continuous, no sharp edges. And then there's one other thing. This is the one everybody always forgets. I'll tell you if you guys can't remember. I just want to see if anyone can dig through their memory and come up with it. What else has to happen to be differentiable? Oh, super, super close. James has almost got it. There we go, vertical. It can't be vertical. If you have a vertical tangent line, the slope of a vertical line is undefined. So by definition, undefined means you're not gonna get a derivative there. Good, nice job, guys. All right, so anyway, function has to be continuous and differentiable. Then there must be at least one value x on the open interval. Now notice that's the open interval, so the endpoints don't count. Maybe even make yourself a note. No endpoints. Because this comes up. If you get an answer that's one of the endpoints, you have to dismiss it. It won't count as an answer. It has to be within the interval. There's going to be one x value in there such that this thing is true. All right, so this is a derivative. Derivative means instantaneous rate of change. So our instantaneous rate of change equals our derivative. And then this is the formula for a slope. You subtract the y values, you subtract the x values. So that would be an average rate of change. So it is a place where the instantaneous rate of change equals the average rate of change. And the way I remember this one is mean means average. So that makes me think average rate of change, if that helps at all, for mean value theorem. But this theorem is really applicable. This is basically like saying, the real world example I always bring up with this is, say you went on a road trip and you averaged over the several hours of your road trip, you averaged 50 miles an hour. That was your average. Like sometimes you were faster than that, sometimes you were slower, but you averaged 50. That means at some point you went 50. Like at some point you had an instantaneous rate of change of 50 miles an hour. If you averaged that, you had to have gone that at some point. And here's just a visual, if you're like a real visual person like me. Again, I'm just going to draw something that goes up and comes back down. It's really not important as long as it's continuous and differentiable. Just draw yourself anything. And we're going to have this interval a to b. And so here's my point at A, here's my point at B. If I connect those, that is the average rate of change. That's just the slope between, the slope of a secant line. It's between 2 points on the graph. Now what this theorem says is that somewhere in between here, there's gonna be a value where, and I think mine's gonna be like right about here, where the instantaneous rate of change would be the same. You see how those are parallel? So there's our instantaneous rate of change. So there's some x value where that is going to occur. This x value has to exist somewhere on there. Out of all the ones we talk about today, this is probably the most important. This is the one that will like come up the most often. All right, and then lastly, Rolle's theorem is named after this guy Rolle. All the theorems are pretty much named exactly what they mean or after the person that came up with them. So conditions for this: a function has to be continuous on the closed interval a to b, and then differentiable on the open interval a to b, and f of a equals f of b. So there's 3 conditions for that. And this last one means that you start and end at the same place. So you come back to wherever you started. So if all that's true, then there's at least one value on the interval where the function has a horizontal tangent line. So let's draw a picture for this one as well. This is really just a specific version of mean value theorem, specifically where the slope is 0. So it's basically just a subset of mean value theorem. So if we have our interval a to b, I'm going to have to be a little bit more careful with this one because they have to, you know, be the same. We're going to start and end at the same place. So f of a equals f of b. These are the same. And so if I connect those, I get a slope of 0. So that's the average rate of change that is 0. And so this theorem is saying at some point on that interval, you're going to get a tangent line that also has a slope of 0. So that x value has to exist. So again, it is mean value theorem, just specifically with a slope of 0. But it makes sense, and I'm going to write it out in words here too. You know, in plain English, if you start and end at the same place, then you must have turned around, is essentially what this is saying. And when you turn around and get that peak value, you're going to get a horizontal tangent line. So if the function starts and ends at the same value, then it turned around. So if the function starts and ends at the same value, then it had to have turned around. And so when you are actually working a problem like this out, like if you're actually doing an example, to check for a horizontal tangent line, that's where the slope of the tangent line is 0. And so you would set your derivative equal to 0. So that's what you're solving for, which those are the critical points. And we talked about that when we looked at graphing derivatives. Do you remember when we looked at the graphs and we put in all of those horizontal tangent lines? Those were the critical points. That's essentially what you're finding here.